Hello everyone, and welcome to today's Chem lesson. Today we're going to talk a little bit about reference table I, right, which gives us delta H heat of reaction values for a bunch of different reactions, and how we can use table I to answer some questions. We're also going to talk about the idea of spontaneity, and what it means for a reaction to be spontaneous. Right, we're going to introduce the idea of entropy, which is a new vocab word and a new concept that we're going to talk about. All of which is for this video, right? To get started, we're going to look at table I. Table I, at its core, gives you a list of reactions and their delta H values. Right? It gives you heats of reaction at 101.3 kPa and 298 Kelvin. Now remember, this is STP, standard temperature and pressure. Right? This is not meant to throw you off. This is not meant to be anything other than reminding you that this is just at the baseline for comparison to everything else. The important thing that we get from looking at table I right before we get into it is this asterisk. It directs us down to the very bottom of table I, which I have cut out for us, and it points you to this sentence here. Delta H values are based on molar quantities represented in the equations. A minus sign indicates an exothermic reaction. So there are two very important things here. First, you do not need to memorize whether a delta H being positive or negative is endo or exothermic. It is literally told to you on table I. It tells you a negative delta H is exothermic. Done. Piece of information given directly to you, handed to you in this 12-page silver plate that is the reference table. The other thing, this idea of a molar quantity is going to kind of reawaken some of the vocab that we left behind in Unit 7, in our Math of Chem unit. Right, we're going to look at that. Right. The regions, when it asks you questions and asks you about table I, will ask you whether the reaction is endo or exothermic. It can ask you about how much energy is absorbed or released, how much energy is needed in order to do something, or how much energy is given when you do something. All of which we're going to look at before the end of this video. But first, I have pulled out for us two pieces of table I. Alright, just two rows of table I. This shows us an exothermic reaction, right? Negative delta H is exothermic. And this shows us an endothermic reaction. A positive delta H is endothermic. But we're not always going to see reactions written out in reaction form. Every now and again, they are given to us in word form. I can rewrite this equation. I can talk about this equation and say the combustion of 1 mole of CH4 produces 890 kilojoules of energy. And I can rewrite this reaction, say this synthesis of 1 mole of C2H4 requires 52.4 kilojoules of energy. Now, there are no tricks, there are no typos in this sentence at all. But where did the sign go? Right, this is a negative delta H. Where's the negative here? This is a positive delta H. Where's the positive here? Where did those signs go? And the answer is the sign is right here. All the sign does, right, all the positive or the negative sign does for a delta H value is tell us whether a reaction is endo or exothermic. And what do we know about exothermic reactions? We know that exothermic reactions release or produce or create energy. And so as long as we have a word here that signifies production or release or creation of energy, we don't need that sign. The sign tells us exothermic. This word tells us exothermic. And the same thing applies here. An endothermic reaction absorbs or requires or needs energy in order to happen. This word tells us that this is an endothermic reaction. Right? The word becomes the context that we need to know the piece of information that the sign tells us. Right? Think about it. You are walking through the hallway. Right? You're walking to the store. And you drop $1 from your pocket. Do you say, I dropped -$1? Does that make sense to say I dropped -$1? No, it doesn't, because the word dropped lets the person who you're talking to know that you have lost that dollar. You are down $1. You have $1 less than when you started. I was walking to the store and I picked up $10. Would you say I picked up positive $10? No, you wouldn't, because the words do that for you. Saying I picked up $10 is telling the person who you were talking to that you gained, you have 10 more than when you started with. Right? The words become the sign, and the sign becomes the word. Right? It's just for the context. Now, there's one more way we can see things, reactions written, and it's like this. I can rewrite the reaction and have the energy as part of the reaction. Now again, there's no negative sign here. There's no positive sign here. Right? The sign is always pluses in chemical reactions. Right? We can never have a minus in a chemical reaction. So what part of the way these reactions are written give you this context of endo and exothermic? In this case, it's the side of the reaction that the energy is on. In our first reaction, energy is a product. Right? Products are the things that we make, that we create, that we release. So if we're saying energy is a product, that means we are saying energy is created. Energy is produced. Energy is released. In our second example, energy is on the left side. Energy is a reactant. And when we look at reactants, those are the things that you need in order to start the reaction. So here we say energy is needed. Energy is required. Energy is necessary in order for this reaction to happen. Right? So again, we are getting endo and exothermic. Right? This is endothermic. This is exothermic. We are getting that information not from the sign of delta H, but from the placement and from the context that is given to us in the reaction. We're getting endo and exothermic from the context of the words that are given to us in the sentence. We are getting exo and endothermic from the sign of delta H. But what about the idea of a molar quantity, right? That's what started us down this whole path anyway, right? The thing that it says on the asterisk for table I. If these two sentences are true, and 1 mole of CH4 produces 890.4 kilojoules of energy, what would it be if we were combusting 2 moles? What would it be if instead of creating 1 mole, we were creating 2 moles? We would double both of these answers. If 1 mole creates 890, 2 moles creates 1780, right? Doubling the amount of energy. If I had put a 3 or a 4 or a 7 or an 8, I would be multiplying this value by 3 or 4 or 7 or 8. The value is tied to the equation as it is written. Just like if we were to take this reaction and say, well, what if I made 4 moles of water? Then I would take all of my coefficients and double them. And I would take this value and I would double it as well. If I took all of these values and cut them in half, I would cut the delta H in half as well. If I multiplied them all by 3, I would multiply delta H by 3 as well. It is a molar quantity. It is tied to the amount of moles, right? Remember, those are our coefficients that are created or released or absorbed with each substance. So sometimes you're going to be asked to manipulate values from table I. Right, let's look at this one. How much energy is produced when 2 moles of NaOH dissolve in water? Find it on table I. See if you can get your answer. Our answer here becomes 89.02 because table I tells us that 1 mole is 44.51 kilojoules. Right, if we are going to get 2 moles to dissolve, we need to double this value. Simple as that. Now, table I is not the only thing we're here to talk about today. We're also here to talk a little bit about spontaneity. Right, before we do that, let's take a look at one more problem. Or actually, a couple more problems. According to table I, how much energy is released when aluminum and oxygen react to create aluminum oxide? Now, you should be able to know what each of these things are so you can recognize the reaction. Just in case you don't, there's a little cheat sheet. Here our answer is negative 3351. The negative sign, not totally necessary here because we do have that word given to us already, right? How much energy is released. We already know that this is going to be an exothermic reaction, so we don't actually need the negatives for any of these bits. Right. Put there in the problem, so leave them. What about this one? Again, how much energy is released when hydrogen and oxygen react to create liquid water? Now this one is a little bit tricky, so pay attention. The thing that makes this one tricky is that on table I, there are a couple of different options for creating water. If we want to create liquid water, we need to pull the value that talks about H2O liquid, not H2O gas, right? Not H2O solid, right? And we're not looking at H plus and OH minus making water. We're looking at hydrogen and oxygen reacting to create it. Right? So we're not looking at this reaction, and we're not looking at this reaction. Right? We want H2 and O2 making liquid water, not hydronium and hydroxide, and not making gaseous water. In the other two problems, they did not tell you how many moles there were. So you're just going off of table I, the numbers they give you. Here they tell you 1 mole is created, and so you need to take that into account. .5 kilojoules is our answer here. Right? How much energy is absorbed? That's an endothermic reaction. We're looking for the positive value. 1 mole means we're going to take the 53 that they give us and cut it in half because it makes 2 moles on table I. Right? Table I shows 2 moles of HI being formed. If we want 1, we want half that value. Again, here they give you an amount of moles, so make sure you take that into account. Our answer here being negative 787, doubling the value that they give us on the table because the value on the table gives us 1 mole of CO2. Right, 1 mole of CO2 doubled to give us our 787. Now this is a 2-part video, right? We're not just here to talk about table I, we're here to also look at the idea of entropy. Some reactions occur on their own, right? You leave it out and it happens. It's spontaneous. In order for this to happen, we are looking for products having lower potential energy and/or, right? So sometimes the entropy plays a factor, sometimes it doesn't. Sometimes potential energy plays a factor, sometimes it doesn't, right? We're looking for these 2 things to happen. Lower potential energy for the products means we're looking for an exothermic reaction. Right? That's just a fact. Entropy, now this is the first time we're seeing the word. Entropy is the term that we use to describe randomness or chaos. Right? It's a weird thing to define, it's a weird thing to describe because we're used to science being not about chaos or randomness, right? Science is about order. Science is about figuring things out. It shouldn't be about randomness. It shouldn't be about chaos, right? That's the thing that we get in our heads. But there's a bit of this that makes a lot of sense if we actually take the time to think about it. So first, let's try to answer this question. What kind of phase changes? What are the 3 phase changes that result in higher entropy? That result in something having more chaos or randomness? Right? We're only saying phase changes right now. Those phase changes are melting, boiling, and subliming, going from a solid to a liquid to a gas, or a solid straight to a gas. Those are the 3 phase changes that will result in higher entropy. Now, why? Let's look at entropy with a little bit more of a lens here. We're looking at melting, boiling, subliming. Those are the things that have the most entropy. How can we explain entropy in a way that makes sense to us? Imagine you have a camera, right? This is your camera. It's wonderful. It's perfect. It can take pictures of things at the atomic level. Right? If you aim it at an ice cube, you will take pictures of the water molecules and be able to see the actual water molecules. Right? It's got 10 to the 18th times zoom. Right? You can get crazy detail from this thing. If you took a picture of a solid, you would get 3 pictures that look pretty much the same. Not identical, but very similar. Right? We know that solids have their particles arranged in nice orderly rows and columns. And so if we took a picture of a solid, we would see, these particles arranged in nice orderly rows and columns. Are these pictures identical? No, they're not. There are slight differences between them. And that's fine. But there's not a lot of randomness here. If you took 10 billion pictures, they would all be very similar to each other. Now, what if we took a picture, right, these same pictures of liquid particles? Right, I drew 9 particles in each of these boxes, so let's keep 9 as our number here. If we got 9 liquid particles, we would have much more randomness. These pictures are now very different from one another. And if I took 10 billion pictures, each one would be more different when we compare them than the ones for the solid would be. When we get to a gas, the pictures are all incredibly different. And as we go down from solid to a gas, these pictures get increasingly different from each other. Can you predict a picture of a solid, right? You take these three, can you predict what the fourth one will look like? Yes, absolutely. How close are you going to be to your prediction? Pretty close, because there's not a lot of difference between them. Can you predict what the particles of the gas will look like if you take a picture? Absolutely not. Because those gas particles are moving so quickly and can fill up their whole container, you have infinitely more possible pictures that you can get of a gas. Gases are much more chaotic, much more random than liquids or solids. Right? Solids have the least entropy, and gases have the most entropy. Liquids somewhere in the middle. They're pretty random. There's a lot of different positions for these particles to be in, but they're still limited to the bottom chunk of this container, right? Because they're not going to boil. They're not going to become gas. They have to take the shape of their container. But gases fill their container. There's so many more possible orientations for these gas particles to be in. And that's what we're talking about when we're talking about randomness. When we're talking about chaos. We're talking about how can these particles be arranged in a way where they are different from what they were. And how likely is it that they are different from what they were a second ago, 10 seconds ago, 20 seconds ago? Right? For solids, they're not going to change that much. They're vibrating just slightly. They're moving very, very, very slightly. So they're going to be pretty much the same thing throughout your pictures. Alright, let's take a look at a practice problem for this. Which one of these changes represents an increase of entropy? If we want an increase in entropy, we want to go from solid to liquid to gas, right? We want to go up the heating curve. We want to get towards gas because gases are very chaotic, very random. Solid to a gas. That looks like a good option. I'm going to mark this one. Right, we like that one. Gas to a liquid. That's getting less entropy. That's not a good choice for us. This is decreasing entropy. Gas to a liquid. Again, same thing as choice 2. This is decreasing entropy. We don't like that. Choice 4, from a liquid to a solid. Right, that's also going the opposite way from where we want to go. This is also decreasing entropy. Each of these choices, choice 2, 3, and 4, give us particles that are more predictable. Liquids are more predictable than a gas. If I want to take that picture and predict where those particles are going to be. Liquids are easier to predict than gases. Solids are easier to predict than liquids. Our answer here, which one gives us something that is less predictable, more chaotic, more random, is choice 1. Going from a solid, nice orderly rows and columns, very predictable, very straightforward, to a gas, filling the container, bouncing off the walls, moving very quickly, very chaotic, very unpredictable. Lots of entropy. With that, we're actually done with this lesson. We're done with this video. The next time you see me, or hear me I should say, we're going to be talking about equilibrium. But that's not for right now. For right now, have a fantastic